start my introduction. It's my pleasure today to introduce Dr. Kamber Schwarz. She is a candidate for our Astromaterials and Solar System Formation position. Currently, she is a postdoctoral researcher at the Max-Planck-Institut for Astronomy in Heidelberg, Germany. She's been there since fall 2021. She's working there as part of the James Webb Space Telescope Guaranteed Observing Time team. Prior to that, she was a Sagan postdoctoral fellow at the University of Arizona from 2018 to 2021. She received her PhD in astronomy and astrophysics from the University of Michigan in 2018, and she graduated cum laude in honors with a BS in astronomy and physics from the University of Arizona in 2012. So almost happy 10th anniversary. Kamber is an expert in modeling the chemical evolution of planet-forming disks and an observational astronomer as well. And she uses observatories such as ALMA and James Webb Space Telescope. She combines these tools to characterize the molecular content of protoplanetary disks and identifies physical processes and conditions that influence disk composition. Her results, she places her results of the protoplanetary disk composition into a broader context of the chemistry and interstellar medium, as well as the chemical composition of material available for forming planets, which we'll hear about today. Attesting to Kamber's standing in the field, she is the lead scientist for the Protoplanetary Disk Scientist on the OASIS mission, which is a proposed mission that will study the chemistry of protoplanetary disks if hopefully and successfully funded. Her talk today is, the title of her talk today is The Evolution of Volatile Carbon During Planet Formation. Take it away, Kamber.
All right, thank you very much, Jeff. So I will share my screen. Does everyone see that all right?
Looks good.
Great.
Yeah.
Okay. So as Jeff said, I'm going to talk about volatile carbon during planet formation. And for me, a volatile is going to be a molecular species that is in the gas phase at temperatures from a few tens to a few hundred Kelvin. So in today's talk, there are three main questions that I'm going to be addressing. The first is, how massive are protoplanetary disks? The second is, what form is carbon in these disks? And then the third is, when and where do the composition of disks change? So to put these objects into context, we first have this summary plot here. So stars and the planets around them are formed from clouds of gas and dust in the interstellar medium, or ISM, which will collapse to form a central protostar, a envelope of infalling material, and eventually a disk in Keplerian rotation around the protostar. I will sometimes refer to these as class 0 and class 1 objects. Eventually, the envelope disperses, and you are left with an exposed protoplanetary disk. These are sometimes called class 2 objects. Eventually, disk as well will disperse, leaving behind a system of planets around a central star. So, protoplanetary disks are the site of planet formation, and my work, as well as much of the work in astronomy, has the ultimate goal of defining the habitability of exoplanets. So when we look at planets around other stars directly, we can measure a small fraction of their properties. In the very best case, you can detect a couple of trace molecular species in the atmosphere. And if it has an inclination that allows you to get both the radius and the mass of the planet, you can get its bulk density. Now, in the solar system, we of course have a much more detailed picture of the composition of planets. We have the only known example of a habitable planet in the Earth, and we're able to study the composition of solid materials with exquisite detail, both by remote observations of solar system bodies and by sampling material that's fallen to Earth as meteorites or been returned in sample return missions. Because we have this detailed information, we also have a pretty good handle on the formation timescales of these solids. And through studies of the Earth and other planets, we have some idea of the workings of the planet interiors. So all of these things are really important for planet habitability, but is information that we cannot discern for exoplanets. So my work with protoplanetary disks is really about connecting these two fields, in particular by looking at the chemical structure and chemical evolution of planet-forming material before it's incorporated into planets. Now, the most basic question that we can ask about a protoplanetary disk is, how massive is it? And this ends up being a deceptively difficult question to answer. So about 99% of the total mass of a protoplanetary disk is in the form of molecular hydrogen gas. However, because these disks are cold and because H2 does not have a dipole moment, we are not able to see emission from the majority of the H2 gas. Less than 1% of the mass is going to be in solid particles, which we sometimes refer to as dust. And these can be observed as long as they are roughly smaller than centimeter size, as is shown in this figure here. And then less than 0.01% of the mass is in other gaseous species, with the brightest of these species often being carbon monoxide or CO. And I should mention that with ALMA, we now know that the observable dust disk in these systems is much smaller than the observable gas disk as traced by CO. So this is real data from the same system, but showing dust and showing CO gas. So typically, if we want to determine the mass of a disk, we use one of these two options. We either start with our dust continuum, and we assume that the mass of the dust is proportional to the observed flux, which is a good assumption as long as that dust is optically thin. And then we assume a gas to dust ratio, typically of 100, based on measurements in the ISM to get a total H2 gas mass. Alternatively, we can take our CO emission and assume that the column density of CO, so the amount of CO that we have, is proportional to the integrated intensity of that emission, which is what is shown here. And that is also a good assumption as long as this emission is optically thin. We then assume a CO to H2 ratio of 10 to the minus 4, once again, based on ISM measurements to get a total gas mass. The problem is that these two methods for determining disk mass do not agree with each other. So here I have the gas mass derived from CO on the y-axis and the gas mass derived from dust on the x-axis. And each of these points is a disk that has been observed in both CO and dust and the resulting measurement. The dashed line here shows where these points would fall if the two measurements agreed with each other. And you can see that for the vast majority of systems where we have both these observations, they don't agree. And CO tends to give us a lower mass than dust. So this is telling us that the CO gas is underabundant relative to the small dust. What this doesn't tell us is if all of the gas is underabundant or if it's just the CO itself. So we have two methods to measure disk mass. They aren't agreeing, and we need some way to break this tie. So one option is actually a rare isotopolog of H2, which is HD. So one of our hydrogen atoms has been replaced with a deuterium. This allows for a dipole moment, which emits in the mid-infrared. And the HD 1 to 0 ground state rotational transition has been observed for 3 protoplanetary disks using the Space Observatory Herschel. And if we take these HD measurements, we are able to get disk masses for these disks, which are listed here. You'll notice that all 3 of these disks are rather massive. So they are either of order or an order of magnitude more massive than the minimum mass solar nebula. Okay, so a word of caution on using HD as a mass tracer. So there is a strong abundance temperature generosity between the properties you assume and the flux that you get out. So what this plot is showing is temperature of the emitting gas on the y-axis and the amount of gas warmer than 20 K, since HD does not emit at temperatures below 20 K, on the x-axis. And the coloring shows the flux that you will get from your HD line. And the black line here shows all the combinations that are consistent with our detection of HD in the protoplanetary disk TW Hydra. So if you're going to try to use HD to derive gas masses, your end result is going to be very sensitive to the temperature you assume. So you need to understand the temperature structure. And while we seem to be having some problems with CO as a mass tracer, CO is actually a really excellent temperature tracer. So this is an illustration of a cross-section of a protoplanetary disk. And we have the emitting region of HD, and then we have the emitting region of CO broken down by the rotational or row vibrational transition. And you can see that the various CO transitions are going to be emitting from the same region as HD. In addition, CO also does not emit below 20 K, in this case, because it is frozen out as ices. So we can use multiple observations of different CO transitions to map out the temperature of the gas in the HD emitting region. In particular, with a high resolution facility, such as the Atacama Large Millimeter submillimeter array, or ALMA, we are actually able to spatially resolve these protoplanetary disks, which really helps building a temperature map. So, as I mentioned at the beginning of the talk, disks are in Keplerian rotation. This means that emission from the part of the disk that is moving away from us is going to be Doppler redshifted, and the part of the disk moving towards us is going to be blue shifted, as is shown in this map of actual CO data, where the coloring just shows the peak velocity of the CO emission at a given location. You can also see this if you step through your emission map in chunks of velocity space. So we have emission primarily from one side of the disk, and then as we move to higher velocities, from the other side of the disk. And in particular, I want to point out that when we have these really high resolution observations, we are able to see these sort of ellipses of bright emission. So we see one here, and then fainter, we see one here in a given channel. And what we're actually seeing here is the near side of the protoplanetary disk, CO gas, and then the far side as well. And we don't see emission from the region between because this is where the CO is frozen out as ice. So we know the precise location of this emission as a function of both radius and height in the disk. So this schematic is just a cartoon explaining what I just said on the last slide. So we have an emission layer for the most common isotope of CO, 12CO. This tends to come from the top of the molecular surface. And then for rarer isotopologues of the same transition, so these are things like 13CO and C18O, your emission tends to come from right above the freeze-out layer. And we're able to then back out temperature profiles that give us not only the temperature at a given radius, but the temperature at a given height. And by probing different transitions of CO, we're probing different heights in the disk, building up a two-dimensional temperature map of the system. So I was recently part of an ALMA large program called Molecules with ALMA at Planet Forming Scales, or MAPS. And my role in this program was to take all of the CO transitions for one particular disk, GM-Auriga, and build up a temperature map. And I was interested in this particular source because GM-Auriga is one of the three sources for which we have an HD detection. So I combined this spatially unresolved HD detection with 6 CO transitions from MAPS, as well as 5 CO transitions from my own ALMA program for a total of 11 different CO lines. And then I built a physical chemical model to reproduce the flux and distribution of all of these observations with the ultimate goal of understanding the H2, CO, and gas temperature distribution in 2 dimensions. So a quick primer on the disk GM-Auriga. So this is a 3 million year old transition disk, which means that the dust has been cleared from the small radii, as you can clearly see in this image of the dust emission. You'll also notice that the dust emission has this ring structure. And what this tells us is that for dust that is roughly 1 millimeter in size, there is an overdensity followed by an underdensity, followed by an overdensity in the millimeter dust grains. This dust disk extends out to 260 AU, or 260 times the distance between the Earth and the Sun, while the gas disk extends to 650 AU. So in modeling this system, we include a model that can reproduce this dust substructure based on previous work by Macias et al. In 2018 that I was also involved in. And the modeling process here is we start with the spectral energy distribution, which tells us the total flux as a function of wavelength and is going to be probing the dust properties in the disk. Once that is settled, we feed it into a radiative transfer code called RADMC3D, which includes the dust structure and will give us a abundance and temperature model. That is then passed to a thermochemical modeling program, which is going to solve a large network of chemical reactions to give us the abundances of various gas phase molecules. We take the results for CO and AD and run line radiative transfer to come up with synthetic observations that we can compare to our models or to the real observations. And then we modify the physical parameters of our disk and the amount of CO that we start with and iterate until we get a good fit to the data. What I'm showing here are the best fits to the radial intensity profiles So this is the intensity of the line emission as a function of radius in the disk for our 11 transitions of CO. So the blue is the observation with the associated uncertainty in light blue, and then the red is our best fit model. And you can see that this model is doing a good job of fitting the emission profile within the uncertainties for all transitions at most radii. In addition, we are able to reproduce the observed HD flux exactly. Now, in addition to fitting the radial profile, we also try to match the vertical emission layer for the brightest lines, which we were able to extract height information about. So that was the 12CO 2:1, the 13CO 3:2, 2:1, and then the C18O 2:1. Once again, blue is observations, red is models, and we're able to fit within the uncertainty, though our modeled emission layer is slightly below the observed one, or the best fit to the observed one for the 12CO 2:1 and the 13CO 3:2. We are then able to extract temperature as a function of radius and height from these observations, as I showed a few slides ago. So the points here are the measured temperature from these lines. And then the background is the gas temperature map for our best fit model. So we're doing a decent job of reproducing what was measured, though our disk is actually slightly warmer than what the observations are telling us by a few Kelvin. So what this best fit model tells us about this protoplanetary disk is first that it is very massive. So it has a total disk gas mass of about 0.2 solar masses, which is a large fraction of the mass of the central star, 1.1 solar masses. We also find that the gas to dust mass ratio is 290, which is larger than the value of 100 that is usually assumed. So this to me says that some fraction of the dust, the solids in this system have grown beyond centimeter sizes, perhaps to the size of asteroids, comets, or maybe even planets. We also find that this disk is very cold. So even with our slightly warm model, 32% of the disk by mass is cooler than 20 K. We need this low gas temperature in order to fit the temperatures that we're measuring with CO. And because there's this temperature abundance degeneracy in the HD, we therefore need a high total gas mass to match the HD flux. So we have a massive cold disk in Keplerian rotation. And if you know something about the dynamics of these systems, you might wonder if this disk is going to be gravitationally stable against collapse. So to investigate this, we use something called the Toomre Q parameter, which is an indication of whether or not a geometrically thin disk is going to be stable against gravitational collapse. It depends on the temperature of the disk and the surface density, both of which we have from our model. So we can plug those into the equation and get a Q value that is shown here as a function of radius. Now, for a disk like GM Auriga, which is not actually geometrically thin, you can start to have instabilities develop for Q values less than 1.7, at least according to models. And we do see a dip below this 1.7 value around 84 AU, which happens to correspond to one of our dust rings. Now, we don't see any non-axis symmetric features that would be sort of a smoking gun for instability. However, if there is a planet nearby, perhaps carving out this ring feature, the heat from that planet could actually suppress any asymmetric features. Another caveat to this is that our observations of the CO do not reach directly to the disk midplane where most of the mass resides. And so additional analysis, both of models of the dynamics of this particular disk and better measurements of the midplane temperature are needed. And that is something I'm currently working on with my collaborator, Alexandra Kuznetsova. So with our model, we can also measure the amount of CO in the protoplanetary disk as a function of radius. And what I'm showing here is the amount of CO depletion relative to what we see in the ISM. And what we find is that everywhere in this disk, the CO is depleted by about a factor of 10 inside of 100 AU, and then a factor of 10 to 100 in the outer regions of the disk. Now, this wasn't super surprising. We had found this for other disks before. In particular, I showed this for the first time using another protoplanetary disk, TW Hydra. And while you have this similar trend of a higher CO abundance at small radii and a lower CO abundance at large radii, the absolute amount of depletion in these two systems is different. So I want to point out that not only will the amount of CO gas relative to what you expect vary as a function of radius within a given disk, but it will also vary from disk to disk. So if we use our HD plus temperature to get gas masses, and then we measure the CO abundance relative to H2 in the three systems where we have an HD detection, we find that it is CO and not the total gas which is missing from this system. If we assume that this is true for all of the disks that I showed earlier, where the CO-based and the dust-based measurements disagreed, then it appears that CO abundance being below ISM values is actually very common, as is shown in this histogram on the distribution of CO abundances. However, there's also an two order of magnitude variation in the amount of CO in these disks relative to what we expect. So the amount of carbon in the gas is varying from disk to disk and also varying within an individual disk, which raises the question, what is happening to volatile carbon in protoplanetary disks? Now, the most simplified picture of carbon in protoplanetary disks is that the majority of it, 63%, should be in gas, CO gas in particular. 12% should be in carbon dioxide, and then about 25% should be in grains. Often when we're trying to connect the disk composition to the planets that will form in this disk, we use the C/O ratio. So the amount of carbon relative to oxygen available in a given disk. This is something that was first proposed by Oberg et al. In 2011. And in the simplest interpretation, the only thing that is going to change your CO abundance is the location of snow lines, also called frost lines or evaporation fronts. And this is where a particular species goes from being primarily in the ice in the outer cooler disk to primarily in the gas in the hotter inner disk. So here we have a C/O ratio of 1 after we are inside the CO snow line, because most of our carbon and oxygen are in CO. And then as we see the return of CO2 and water, this C/O ratio drops. And the idea is that if you have a gas giant accreting its atmosphere between the water and the CO2 snow lines, then it should have a C to O ratio initially of about 0.8. However, this picture is overly simplified, and the reality is that these ratios are going to be altered by dynamics and chemistry, as shown in this chemical model, which is once again showing us the C over O ratio, but now as a function of time in the model. So there are a variety of mechanisms that can remove CO from the gas disk. And they fall into two basic categories. There are the physical mechanisms. So these are things like photoevaporative winds stripping the gas from the disk, though this would not explain the low CO abundance relative to H2. You can have vertical mixing of gas down towards the midplane, which will preferentially remove CO from the upper layers that we're observing with facilities such as ALMA. You can then have these, the midplane grains that the CO is frozen out onto, growing, which will trap ice in their interior. And then you can have a combination of the settling of icy grains, growth to larger sizes, and drift inwards, which will deplete the outer regions of your disk of volatile gas phase species. The other category are the chemical CO depletion mechanisms, and there have been various studies that claim to explain these low CO values by the processing into, say, gas phase hydrocarbons in the presence of ionization, into CO2 and methanol ices, or even into more complex icy organic material. However, all of these modeling studies assume different physical properties for their protoplanetary disks and come up with different answers for where the carbon has gone. So much of my work as a graduate student focused on trying to understand what physical conditions lead to chemical reprocessing of CO. So to do this, we ran a grid of chemical models for a large range of physical disk conditions. So we looked at different total gas masses. We looked at different dust grain size populations. We looked at different temperatures for the disks. We looked at different incident X-ray fluxes. And we looked at different UV and cosmic ray ionization rates as well. So we ended up having 198 unique physical models that we then ran the chemistry on top of. So this particular chemical code is a code that runs the chemistry at each radius independently, and further breaks down the radius into 45 vertical zones with no mixing of material between those zones. So this is a static physical model that we're running chemistry on top of. Our chemical reaction network is quite large and includes reactions such as photochemistry, grain surface chemistry of ices, ion-induced chemistry, self-shielding of H2 and CO. There's also the possibility to include different isotopes, so say deuterium or carbon-13, though those were not used in this particular study due to the increased runtime. In this study, we start with a CO abundance relative to H2 of 2 × 10⁻⁴, and we let the chemistry evolve for 6 million years. So this right here is a cutout of a disk where each quadrant is showing the abundance of a different molecule in one of my models as a function of height and radius in the disk, where black means high abundance and white means low abundance. And you can see that while we started with the CO being the primary carbon carrier, so this would have all been black at T equals 0. By 6 million years, we have built up a large reservoir of CO2 and methanol ices. However, this only occurred in the models where we had a source of ionization. And the way that ionization leads to this ice buildup is not entirely intuitive. So what happens is that enhanced ionization will increase the amount of H3 plus in your gas. That H3 plus then reacts with CO to form HCO plus, which almost immediately is going to find an electron, recombine, and go back to CO, which sounds like a completely useless process, except that this has freed a hydrogen atom. Some of these hydrogen atoms are going to find their way onto dust grains. And so CO, sometimes even in warm disks or warm areas of the disks, will occasionally freeze out onto a dust surface. And before it can thermally evaporate back into the gas, it will react with one of these extra hydrogens, either in the form of atomic hydrogen, leading eventually to methanol, or in the form of OH, leading to CO2. And because these species are able to stay as ices at higher temperatures than CO, we are removing carbon from the gas phase chemistry, and it is effectively hidden from our observations. However, this scenario where there's enough ionization for this process to happen only occurred in a small fraction of our models. So here I'm showing the distribution of CO abundance in the models compared to what we've observed. This basically only happened when we had either extremely low density disks, so not like GM Auriga, which has a high density, and when we had at least ISM level cosmic ray ionization rates, which is not the case for TW Hydra, which has previously been shown to have a lower ionization rate. Additionally, these depletions to get to what matches the observations often take longer than the typical disk lifetime of 3 million years. And so we need to either combine the chemistry with these dynamic processes that I talked about earlier, or the depletion needs to happen at earlier times. All right, so the combination of dynamics and CO actually can decrease your CO. This is work that I was involved in, led by Sebastian Kreit, where we combined a dust evolution model just with simple CO freeze out. And we were able to get some depletion in the outer disk and then return of CO in the inner disk. And this profile shape looks very similar to what I showed for TW Hydra and GM Auriga earlier. However, the actual amount of depletion actually only agrees with disks like this one shown here, which are around massive stars and therefore much warmer. We need an order of magnitude more depletion to match the amount that we see around cooler, lower mass stars. So that is interesting, because while we can explain the results for massive stars, we can't explain the results for cooler stars without invoking ice chemistry. And it's these cooler stars that we are currently detecting a large number of exoplanets with using the TESS mission. We then added full chemistry to these models, which is shown by the green lines in these plots. And we did find that we could get to that factor of 2 orders of magnitude depletion that we needed to explain observations after 3 million years. However, observations are telling us that in reality, this depletion of CO happens much, much quicker. So now I'm showing the CO abundance relative to H2 as a function of system age, both for individual systems and for the range of values in the Lupus and the Chameleon star-forming regions. And you can see that by 2 million years, we have a factor of 10 to 100 of CO depletion. However, before 1 million years, when the disk is still embedded in its envelope, and when we're somewhere between the formation of CAIs and small bodies like Vesta, the CO abundance actually matches with the range that we see in the ISM. So the observations are telling us that gas phase depletion of carbon occurs early, around the 1 million year mark. And that's interesting because there's also growing evidence that planet formation also starts early. So the best evidence that we have for a planet coexisting with a protoplanetary disk is PDS 70. So here you see a ring of dust in the gaseous disk, and then you see this point right here. And this point is emission coming from the circumplanetary disk of a planet several times the mass of Jupiter that is actively accreting material from the larger disk. Now, this system is 5 million years old, but there's evidence for giant planets in younger systems too. So here I'm showing just a single channel of CO, kind of like what I showed earlier, where you have a surface. But here we have this sort of swerve or break in the emission. And this has been attributed to the gravitational pull of an embedded planet. Now, maybe you don't believe that, but we've seen this in an even younger system where this velocity break also coincides with a dark ring in the small dust, as if this dust has been cleared away by a massive body. Now, these dust rings are ubiquitous in protoplanetary disks, most famously in the first one imaged, HL Tau, which is only 1 to 2 million years old and still has a residual envelope around it. And we're now seeing these dust rings in systems as young as 500,000 years old. And while I'm not convinced that there are planets in all of these systems, I do think that this is evidence for the growth of solid material and that carbon depletion and planet formation are happening simultaneously. So let's look at these young systems surrounded by their envelopes. I previously said that ionization helps with chemistry. And when you still have an infalling material, there are a lot of shocks in the nearby environment that can accelerate cosmic rays to have ionization rates several orders of magnitude above what we see in the ISM. In fact, an ionization rate enhancement has been inferred from free emission along the jets from these young sources in the bow shock of one protostar and in the envelope of infalling material for one protostar, though subsequent follow-up data was not good enough to constrain other sources, which is what's shown here. So I followed this up with new observations of protostellar envelopes, particularly meant to trace ionization. So the molecules that we're looking at here are H13CO plus 1 to 0 and C18O. These are not ALMA observations. This is data from another interferometer called NOEMA in France. And we can use the ratio of these two species to infer an ionization rate because of how HCO plus is formed. So I'm going to go through this quickly because I know that we're running short on time. But suffice it to say that ionization converts CO into HCO plus. And so the ratio of these two species is going to be proportional to the ionization rate. And if we assume, excuse me, sir, the properties for the rest of the terms in this equation, we can get an ionization rate, which is exactly what we did for these three sources. And what we found for an assumed electron abundance proportional to HCO plus, which is a minimum, were ionization rates that peak well above the ISM value of 10 to the minus 17. So we're talking 10 to the minus 12, 10 to the minus 14. And this is consistent with the one other source where we've measured ionization enhancement. Now, I'm currently working on some new models to better constrain the H2 and electron abundances that I need to assume to get these ionization rates. But I hope to expand this study to a much larger sample. Okay, so I propose that the story of carbon in protoplanetary disks is, in the early phases, while you're still surrounded by an envelope, enhanced ionization jumpstarts the gas and ice chemistry, removing carbon from gas phase CO and putting it into CO2 and methanol ices. As this disk cools, the species are freezing out onto dust grains, and we get a large buildup of ices. These grains, as they grow, will settle towards the midplane of the disk and drift inward to small radii. At high temperatures in the terrestrial planet-forming region, they should be enriching the inner disk in carbon. And excitingly, James Webb is likely going to tell us if this story is correct very, very soon. So as part of the JWST GTO program, I am hoping to observe the return of gas phase species such as methane and CO2 in the inner disk, as well as observe ices in the outer disk, and combine this information with my new models to determine the abundance and distribution of carbon in protoplanetary disks. Okay, so to summarize, observations with ALMA tell us that volatile gas, particularly carbon gas, is depleted in protoplanetary disks. The amount of depletion varies with radius in a single disk and also from disk to disk. This depletion occurs early, we think, and is likely driven by higher ionization, something that I'm currently investigating. This depletion is also likely driven by both dynamics and by chemistry in order for it to happen so very quickly. The carbon is likely in volatile ices, and this is something that we will be able to probe with JWST. Thank you.
Thank you, Kamber. That was a fantastic talk. It was interesting to hear how carbon is so important for not only understanding the evolution of the disk, but also its structure and how it influences planet composition. It's great. Do we have any questions for Kamber? Oh, Ryan's got one.
Yeah, thanks, Kamber. That was fantastic. You're telling us about the story of carbon in protoplanetary disks. I was wondering what you think of the role of carbon in organics or refractory carbon. In both of those phases, we have cosmochemical evidence that those were likely inherited from our parent molecular cloud. So what role do you think refractory and organic carbon play?
Right. So there is a question of whether some of the refractory carbon is destroyed and can play with the gas phase chemistry. I have a collaborator who's looked into this. It actually doesn't seem to be important. I think that the timescales in protoplanetary disks that it takes to build up complex organics are so long that it's unlikely that a significant portion of the organics inherited by solar system bodies were synthesized in the protoplanetary disk, unless the ionization rates are like really crazy. However, if we are inheriting that material and it already has some level of complexity, there is the possibility that you can build up additional complexity in the protoplanetary disk phase, having this influx of fresh atoms onto the grain surface, basically.
Great, thank you.
Next up, Hendrik.
So I think you are doing kind of observation and modeling is all like polarization independent.
Mm-hmm.
Can you also do polarization dependent radiation transport and observations, and would that add something?
So ALMA is capable of doing polarized observations. They are a pain. And as far as I know, have only been successfully carried out for the dust continuum and not for molecular lines. So the polarization generally tells us about perhaps the alignment of magnetic fields, perhaps the shape of the dust grains, but for the more chemical side of things is not been very useful.
Thank you.
Any other questions for Kamber?
I have another one if nobody else does. Early in your talk, Kamber, you said that you know part of this work is understanding the total mass of the disk. But when I think about forming rocky planets, I think of the dust component mattering more than the H2 in the system. So is that true? Is like when we think about rocky planets, is it more important to think about dust mass and gas giants, you know, total mass? Is that a fair interpretation?
I would say yes, based on the solar system. However, based on exoplanet systems where we're seeing a lot of like mini Neptune, super Earths, and there's this idea that maybe some of these planets lose their thick atmospheres and then become terrestrial planets later on. Maybe, we don't know. Then the gas would be important. I think that the gas is important in that for small dust grains, those dust grains are coupled to the gas, so the motion of the gas is the motion of the dust. And also, particularly for the molecules, as you have species like water and CO2 coating these dust grains in ices, they change the collisional properties and can hinder or help the formation of more solids, larger solids. So I think that the gas disk is not important for the formation of terrestrial planets, but it is important for the potential habitability and delivery of volatiles to those terrestrial planets.
Great, that's fascinating. Thank you.
Mm-hmm.
And a delivery mechanism of volatiles, particularly water. I like your model. I think it was you ionize HCO and the H sticks to the silicate grains.
Mm-hmm.
Do you have, is that a model that you came up with, or has that been around? I haven't seen it.
Yeah, so it's pretty standard to include some grain surface chemistry in astrophysical chemical models, because otherwise we can't form H2 or water. It needs to happen on the grain surface. But then you get the question of what is the composition of this grain surface, because that's going to affect the binding energy for different species, how well they're able to stay on the surface. So in my models, I typically assume that CO is binding to a CO ice covered surface, which seems to be backed up by observations. And that, but there's also laboratory measurements of what the binding energy is for, say, bare silicates or for water CO2 mixtures. And that's all laboratory astrochemistry work that we can then take the results of and input into our models and tweak as we see appropriate.
Okay. That was going to be another question, is, you know, what kind of models help support that? But I'll go a different direction. And so we have the laboratory models, but what kind of extraterrestrial materials might we seek out to, you know, help support these astrophysical observational models?
Yeah, so I think that understanding the formation timescales of solids relative to the things that we see going on in these protoplanetary disks is really important. So I said that we have evidence that the solids are getting bigger early on in these systems, but there are other interpretations to that data. We don't know that definitively. And in the solar system, we can pretty precisely say, okay, well, we think that CAIs were formed this long ago, and Vesta-sized bodies were formed this long ago, and the core of Mars formed at this point. I think the challenge is finding some sort of marker that we can then apply to these other systems to really say definitively, oh, okay, this system is at the Mars core forming stage. This system is at the chondrite forming stage. And I think that's going to be the challenge, is what is something that we can measure in other systems? Is it an isotope ratio? Is it a dust signature that will tell us where they are in their formation process relative to the solar system? It's something that I think we really, really need to do. And it's going to require communication between the people who observe protoplanetary disks and the people who measure abundances in the solar system.
Great, I like that answer. All right, any other questions for Kamber? All right, with that, I'll thank you one last time. It was a wonderful talk, and have a great rest of your afternoon.
Thank you.
Take care.